infinity along the straight line, but it makes no difference how you go. If you go from A to B, this potential difference, and you go in this way, then VA minus VB is not going to change. And so if now I introduce here a element dl, which is a small vector, and if the local E vector here is like so, at this point here, then VA minus VB is then the integral of E dot dl. In other words, I can replace the R by an L, and you may choose any path that you prefer. And that's the way that we will show you this equation most of the time. So it makes no difference how you march, because we are dealing here with conservative fields. So let's now make the assumption that VA is 150 volts, and that VB, for instance, is 50 volts. So it's a very specific example. What does it mean now? It means that if I put plus Q charge in my pocket, and I come all the way from lobby 7, and I walk up to point B, so Walter Lewin, plus Q charge in his pocket, goes from lobby 7 to point B, I have to do work, and the work I have to do is the product of my charge Q with the potential. So that is Q, the work I have to do is Q times VB. So in this case, it's 50 times Q, whatever that charge is that I have in my pocket. This is in joules. Now, I go from lobby 7 to point A. I have to do more work. I have to do 150 Q joules of work. You can think of it, I first come to A, to B, I'm already exhausted. I have to put in another work to get all the way to point A. So you can imagine if I have this plus Q charge at point A, where it is at a higher potential, it wants to go back all by itself to B. It wants to go from a higher potential to a lower potential. Look, the E vector is in this direction. Positive charge will go to a lower potential. And as it moves from A to B, energy is released. How much energy? Well, this is the amount of work I have done to get to A. This is the amount of work I did to get to B. And so if now the charge goes back from A to B, it's the difference that becomes available in terms of kinetic energy. It's a change in potential energy. And that change in potential energy, so the change in potential energy, when the plus Q charge goes from A to B, that change is Q times VA minus VB. QVB at point B and QVA at point A. So this is the potential energy that is in principle available if the charge moves from A to B. And you remember from 801 the work energy theorem. If we deal with conservative forces, then the sum of potential energy and kinetic energy of an object is the same. That's also true for gravitational forces. In other words, this difference in potential energy that becomes available, like potential energy becomes available when I drop my chalk from a high potential to a low potential, that's converted to kinetic energy. So this difference now is also converted into kinetic energy of that moving charge, and so that would be the kinetic energy at point B minus the kinetic energy at point A, which is really the work energy theorem. It's the conservation of energy. Now, any piece of metal, no matter how crummy or dented it is an equipotential, as long as there is no charge moving inside the metal. And that's obvious that it's an equipotential. Because these charges inside the metal, these electrons, when they experience an electric field, they begin to move immediately in the electric field, and they will move until there is no force on them anymore, and that means they have effectively made the electric field zero. So charges inside a conductor always move automatically in such a way that they kill the electric field inside. If the electric field hadn't been zero yet, they would still be moving. And so each metal that you have, no matter where you bring it, as long as there are no electric currents inside, will always be an equipotential. So I can take a trash can and bring it into an external field, and then very shortly after I've brought it in, when things have calmed down, the trash can will be an equipotential, and the electric field inside the metal will everywhere be zero. So, I could, for instance, attach point A to a trash can, metal trash can. So the whole trash can would be at 150 volts, and I could put point B, make it part of my soda, which is also made of metal. And so the whole soda would be at 50 volts, and the entire trash can would be at 150 volts. I place the whole thing in vacuum, and now I release an electron at point B. An electron. Electron wants to go to higher potential. A proton would go from A to B, electron wants to go from B to A. And so, now, energy is available, the electric potential energy is available, and the electron will start to pick up speed and finally end up at A. Now, how it will travel, I don't know. The electric field configuration is enormously complicated between the can and this trash can. Amazingly complicated. If you were to see the field lines, it would be weird. But if all we want to know is what the kinetic energy is, what the speed is with which this electron reaches the can, so what? Then we can use the work energy theorem and find out immediately what that kinetic energy is. Because the available potential energy is the charge of the electron times the potential difference between these two objects. Well, the charge of the electron is 1.6 times 10 to the minus 19 Coulomb. The potential difference is 100 volts. And that is the difference in kinetic energy. If I assume that I release the electron at zero speed, then I have immediately the